Hello everyone, I welcome you to this learning activity. In this activity, we will tackle spectral indices. We have worked through multi-band images and now know that every spectral band provides a unique perspective on our environment. Combining the spectral bands can yield deeper insights. And this is what we will be doing in this activity, applying arithmetic operations across spectral bands to understand differences in surface materials. We will compute spectral indices and examine how the indices help distinguish or characterize surface types. So we will apply prior knowledge including pseudo color and false color composition. So please make sure you have completed the activities before this one. So what we're going to produce is very similar to this. We're going to produce something similar. So where we are going to generate a spectral index in grayscale, and then we are going to impose colors on the pixels, produce a pseudo color image like you see here. So that is what we're going to do. Now let's head over to the code editor to unpack. Yeah, so once you bring up your code editor and you want to start a new script, you just click. You have to be sure that you have the script tab on, and then you go here and then you are going to create a new file. Okay, so this has been covered in the previous video, so be sure you have watched it. Well, the task we have here is that your boss has given you this image data, a multi-band Sentinel-2 surface reflectance image that was collected on the 28th of April 2024. Okay, so this is the image that are given to you, and this says that is the image ID or the asset ID. So it is an image, not an image collection. It's just one image your boss has given to you, and you have been given the task that using this image, compute and visualize the following spectral indices. The first one is the NDVI, and then this is to assess the health of vegetation in the image. And then we also have the normalized difference moisture index and another normalized difference water index. So these two is to assess moisture in the vegetation or in the soil, or sometimes to see open water on the land. So you use that to assess water. And then another index is to compute the normalized burn ratio to assess fire scar areas. So this is another task then you have been given. And then to track other conditions specifically related to bare soil and places that are free of vegetation or sometimes dead vegetation. You're going to explore the SAVI and then the EVI. So these are common spectral indices you come across. There are heaps of them. So to start with, you have been given this asset ID, and then the task is to compute and visualize these spectral indices. We are going to take two approaches to this. We are going to use a built-in function as much as we can to compute some of these indices, and then we will also write our own expression to define this. Okay, and then compute these indices and then visualize it in single band or grayscale, as well as pseudo color image. So that's what we're going to do. So to start with, so this is a task. You can see that they are all in green because of these two forward slashes. Everything is in green, so you can think of this as comment. They are not going to affect your script at all. Okay, just keep it there. And so what we're going to do, we are now going to start scripting. So the activity start from here. So scripting, properly starts from here. And so the first thing we want to do is that this is the data set that has been given to us. So we're going to copy the ID, and because it says that it's an image, I have to go to the two boxes. The two boxes are here, and you go a lot of two boxes here. And because it says that it's an image, we will be interested in what you will be interested in this function ee.image. So we're going to have ee.image, and then when you click on it, there's a note. It requires arguments, and one of these is just asset ID or the image ID that can be used. But when you go further, you know that it requires a string. So what it means is that I'm going to put in a string here, which means double quotes, and then I'll copy the name of this image ID, and then I'll stick it in here. Okay. So this is what I've done here. So I've sort of created this object, but it is not yet complete because in this software you have to declare object with a var and then object name. So in this case we are going to call it s2, and then we assign the object to it. So once we have got this thing here, this variable is going to stay in the computer memory, and then we are going to use it. So the next thing you want to do is that you want to print this variable. We want to know a little bit more about this data set. So we're going to print this one here, and then you just run this. And then what you're going to do now is that you have to wait for the details to pop up in the console. So once it comes in the console, you just click on the expander. You see the barns here. So we've gone through this in previous videos. So quickly running through this. So we've got 26 bands. Some of the bands are not relevant. They are just for a quality assessment. So we'll be interested in the spectral bands that have got B, starting it. So what it means that we are not going to use all these 26 bands. We need to select the relevant ones and use. So that's what we're going to do next. Okay. So we're going to select bands from here. We're going to select the relevant bands. So we are only selecting band 2, 3, 4, 5, band 2, 3, 4, 8, and so on. So for these are the bands that we're selecting. And then once you run that, you can see that it's going to move from 26 bands that we saw earlier to only 6 bands. These are the bands we've selected. So we've been able to reduce the file size in that case. Okay. So now that we are happy with this, we are going to use this data to compute our vegetation or our spectral indices. Okay. So that is what we're going to do now. So what I'm going to do is that I'm going to hit on the enter key just to give myself some space here. And then once I have got a space, I'm going to now compute the spectral indices. Okay. There are many spectral indices available. There's a lot of them, right? But these ones we are going to cover here, they are just often used. They are very fundamental among all the spectral indices, and you see them a lot. So that's what we're going to show them. But don't be surprised that in future you see a spectral index that we didn't cover in this video, right? So once we have that, we're going to create our first one. Our first activity is to create or to compute the NDVI. So we are going to compute NDVI. Well, to do that, we are going to use the built-in function to do that. So we are dealing with image. So what method here or what function here can we use to compute NDVI? So there's a generic one that we are going to use for now, and then we'll change it later. So there is one that we call the normalized difference. So normalized, there's this method called normalized difference, and this is the one we're going to grab. So I'll gently go through this, and then this is the one. So normalized difference. So we are going to use this method. This method is the workhorse for computing spectral indices related with normalized difference. So once you just click that and just read about it, it says that when you are using this method over an image, you're required to include this argument, which is what band names. And so what are the band names? So the band name is just a list of the bands you want to specify. So once you put in a list of those bands, they are going to compute the index for you by subtracting the second band from the first and then dividing it by the sum of the two bands. Okay, so just a little bit about this will make you understand what you are doing, and then you are able to apply it. So what we're going to do is that we're going to create NDVI. So I'm going to create a variable called NDVI, and then what I'm going to do is that I'm going to bring my image. This is my image here, and I'm going to make one treatment to this image. Apply. This is called apply. And which method I'm applying? I'm applying this method. So I'm going to copy this method here. I'm going to copy this method here, and then I'm going to apply it to the image. So the next thing I need to do is that I need to define these bands, right? And to define these bands, it has explained that I need to provide a list. So a list of names specify the bands to use. So if you go to my image here, I've got these bands here. So what I'm going to do is that I'm going to provide a list of these. So when you say a list, this is going to be a list. A list simply means we need what? Square bracket. Square bracket is indicative of a list. And then what we're going to do is that we'll put the band name. So one of the things you have to do is that you have to look it up. What is the formula for NDVI? So once you step out NDVI formula, you just see that, right? And then it pops up, and then it gives you that, it is actually subtracting the red light from the near infrared light, and whatever you get divided by the sum, right? So this is what we're going to use. So so in Sentinel-2, our infrared light is, our near infrared light is this B8 here. So I'm going to copy this B8 here. I'll copy B8 here, and then I'll stick it there. And then the red light is actually B4. B4 is red light. And then I'm going to also that one there. So I have fulfilled this argument now. So now what I know is that this is going to compute my NDVI for me. And so once I have this, I'm going to print the variable. So I'm going to print to console, right? I'm going to print this NDVI layer to the console. So, and I'm going to print this to the console, and I'm happy with this thing, and then I'm going to click run. So once you click run and you go to bands, you see this is your band. It's going to give you a band, so that is going to be just a single band, and the name of the band is called ND, right? ND. Well, it doesn't make sense to me, so I'll prefer to call it something more intuitively. And so what I would do is that instead of calling it ND, I'll prefer to call it NDVI, to really name the band NDVI, because it's NDVI, not ND, not normalized difference. It is NDVI. So what I'll go to line 22 to do is that I'm going to apply rename the band. So there's a method called rename, and you always can find it here, rename. And then I'm going to rename it as what? NDVI. So I'm just telling the computer that I don't like the name, the default name you have given me. Will you rename as NDVI? And then the computer is going to do that. So I've added this to it, but the print command is going to remain the same. And then when you run it, you see that the only thing you have done is that you have renamed the band from ND to NDVI. Okay. So the other thing you would like to quickly do is to visualize this. So we're going to visualize the NDVI layer. So we're going to visualize it. So this is what we're going to do here. So again, we have done image visualization, so I'm not going to go into it. This is the object, so you need to specify, and then the minimum value and the maximum value. NDVI by theory, the value ranges from -1 to +1. So the minimum value is -1 and maximum is +1. And the layer name, the layer name is what we see here. I like to use double quote for consistency, so that is why I'm doing this, but the single quote will still work. Okay, so and so this is going to print this one out, and so then this is going to give me a pseudo color. So this is going to give me the true color, the true grayscale, which is a single band. So you're going to have a true grayscale color for this first layer here, and then this one here we have assigned colors to the pixels. So how many colors have we assigned to the pixels? 1, 2, 3, 4, 5 to the pixels there. And so once you run it, you are going to see variation between this one here and that one here, but I'm going to run them one after the other. So I'm going to run this one. So I need to zoom out to my study area, which is somewhere in Northern Australia. So this is the NDVI layer, and what this means is that the brighter pixels are greener areas, like they are healthy areas, and then the darker pixels, they may not be vegetation at all, or even if they are in vegetation, if they are vegetation, they may not be healthy. So one of the things you can quickly do is that you can take your inspector tool, and then you just can click any pixel randomly. So this pixel that I selected, the NDVI value is what? 0.6, is about 0.65. So water is not a vegetation, so you can see if I click a pixel, a water pixel, you can see the NDVI is negative, meaning that one, it is not a vegetation at all, and then it's even low, isn't it? So that is how you inspect that. So the other thing you may quickly do is that you see sometimes visually we struggle with grayscale images, so you want to manipulate the pixels here by giving them color, and this is what we call the pseudo color, and this is covered in previous videos, so please just watch it for a lot more details than I'm showing here. So again, you can see this is the original one. Yeah, now we have given it a range of colors, which means that the color palette, if you go to the color palette, it's saying that the very healthy vegetation, they are the ones that they are the green pixels here. So we can see the green pixels here showing healthy vegetation, and the less healthy ones are the yellow pixels there comparatively. So this is how you show NDVI in terms of computing it and displaying it as a grayscale and a pseudo color image. We're going to build on this in the next video. Okay. Yeah. So we're moving on to the next one, and that is going to be the NDMI and the MDWI. So what we're going to do is that because the formula for these other ones, the NDMI, NDWI, and even NBR, they are very similar to the NDVI because they're all normalized difference. So normalized difference, normalized difference, and normalized difference. We're going to use the same thing, So this is where we're going to learn how to modify script in this case, because we're only going to change the bands, same thing, and then rerun it. Okay. So what we're going to do is that first of all, I'm going to copy the whole of this script here. I'm going to copy. Okay, I'll go copy up to this point here. Okay, and then I'm going to this is going to be NDWI, I reckon. And so I'll paste the script here, and then what I'm going to do is I'm going to change this one to MDWI. Sorry, MDWI. Everything is going to remain same, but the formula for NDWI, it requires the green light and the near infrared light, which is B8. So again, you need to look it up. Okay, how do you compute that? Once you know the formula, and then you'll be able to specify the appropriate band. So we need the green light and the near infrared light to compute this NDWI here, which is sort of used for monitoring changes in water, surface water in this case. So here we just change this NDWI, and then in your print also you just change this to that, and so that is what you have done here. And then once you have done this, the next thing is that you want to visualize. Okay, so visualize the NDWI. And so how are we going to visualize? So we're going to bring in the layer we created here, and then give it appropriate name in the layer manager. And then I selected these colors. Selecting colors is completely subjective, but these are the colors I'm saying that, okay, where you go dark blue, it means that there's a lot of water. Blue, also water, but where you see red pixels, it means that place lacks water. Okay, so that is what I'm going to do here, and then I'm going to run this. So just running this. So I'm going to turn off these NDVLAs, and then I'm going to stick with this one here. So you see the water, see what the grayscale, the water body is what brighter. It means that it is high in NDWI, which is okay, because which makes sense, because that is water body. So it's brighter, and then the non-water pixels are a little bit darker. But when you change this and bring in the color, you can see we specify that let the water pixels be blue or dark blue, and then you can see, once you zoom, you can see where the water pixels are in the image, and that is what we have demonstrated here. The next thing we are going to do is to compute the normalized bend ratio. So I'm going to leave this one to you to do it by yourself, but I'm going to do the normalized bend ratio for you. So with the normalized bend ratio, what are we going to do? I'm going to copy the same script. So I'm just going to just identify this as normalized bend ratio, and then I'm going to normalized bend ratio. Okay, so I'm going to copy the script. Where's the script? So I just copy this script here, and then I'm going to modify it. Okay, so I'm going to paste it here, then I'm going to modify it. So to really do that, I need to use band 12. So I'll go back to my console, and I'm going to use band, no, this one here. I'm going to use band 12. So I'm going to use B12 here, which is a shortwave infrared. Again, you need to step out, to Google, to look it up. What is the formula for the normalized bend ratio? So NBR, what is the formula for that? And once you know the formula, you see the kind of bands you need. And I'm just saying that we need band 8, we need band 8 to be, which is the near infrared, and also we need the shortwave infrared. Then we can change this one to NBR, right? NBR, and then from here we are going to print NBR to the console. So this is going to show us the fire scars in the image, if indeed there were fire events in the study area. So you're going to run this, and then once you print it out, the next thing we're going to do is to visualize. So I'm just going to visualize this. So I'm going to shush these ones, okay, just to shush them so that the code run quickly. I'm going to shush these ones and that one there, and then I'm going to run this now. So this is your NBR, your normalized bend ratio in grayscale, right? So and then this is the shadow color. So you can see these are the fast cast, potentially fast cast. Here, over there, these are fast cast. So obviously, you can see by the color palette, we say that dark green, we don't want that one, but we're saying that red, magenta, purple, those ones are the fast cast. And where they are green and dark green, it didn't bend, right? So these places were not bent. The bent places, those ones you see in purple. So red, magenta, purple, they are potentially bent areas. And then here you see them to be bent. Okay. So you can see the places that got fast cast. So that is how you compute this NDVI using the built-in normalized difference method. We are going to look at another method which is more popular than this method and more robust in the next video. Okay.